Hey guys, today we're going to be taking Hess's law one step further than in the last video, and we're going to use Hess's law to discuss the heat of formation of any compound. So let's go ahead and get started. So let's do an example. In this case, we're taking iron solid, that's elemental form iron, and oxygen gas, that's elemental form oxygen, and we're combining them in a chemical reaction to produce iron 3 oxide. Now, in this iron oxide, what we are going to be doing is producing 2 moles of iron oxide for every 4 moles of iron and 3 moles of oxygen. Now, the delta H of this reaction is 1,648.4 kilojoules per mole of reaction. That means for every 2 moles of iron oxide that is created, we are going to use 1,648 kilojoules, which means the heat of formation for iron oxide would be the equivalent amount of energy necessary for 1 mole. All we have to do is take this value, 1,648.4, and divide it by 2 in order to get how much energy it would take to form one of these. Another way we can think about this, going back to our Hess's law idea, is the fact that if we just divided this whole thing by 2, because now what you see, just like with Hess's law, when we divided everything in the coefficients, we also divide our delta H by 2, and we get our reaction here, which is the formation of 1 mole of Fe2O3, or iron 3 oxide. All right, let's do a practice problem. We're connecting the heats of formation to the enthalpy of an overall reaction. So here I'm given the heats of formation of all compounds in this, except for one, the oxygen. But remember, that's elemental form, which means its heat of formation is 0. So what I have here are heats of formation of both reactants and products. But remember, reactants aren't forming, they're breaking. So the connection to Hess's law here is the understanding that the heat of formation in the opposite direction would be a positive 83.8 of my C2H6, which is actually being broken apart. So what I need to do is I need to take my 83.8, multiply it by 2, and make it positive. Okay? This is going to be the heat of those reactants, or that one reactant in this case, breaking apart. That's going to give me a change in enthalpy of my reactants of 167.6 kilojoules per mole. That means to break apart the 2 molecules of C2H6, it's going to take this many energies per mole of that. Now, we're going to then look at my products. The products are forming, so I'm not flipping the sign here. I'm just multiplying by my coefficients. All right? So what I'm going to do is I'm going to take my water, my carbon dioxide, multiply each by the coefficients, okay? And then I'm going to add those values together. Okay, so it's negative 393.5 times 4. That's going to be my carbon dioxide heat of formation times 4. It's negative because, remember, these are actually forming. The products are forming. And water is negative 285.8, and I'm going to multiply that by 6. So the total delta H of my products is negative 3,288.2. What this means is in the course of this reaction, I had to put in 167.6 kilojoules to break apart my reactants. I then got out 3,288.2 kilojoules per mole when I formed these two products. The difference between them, in other words, having to put this in and getting this out, is going to tell me the delta H of my overall reaction. Okay? So in other words, what we're going to do is we're going to take my negative 3,288.2 and my 167.6, and the difference between them, which is 3,121.2 kilojoules per mole, gives me the overall delta H of my reaction. So in this case, what we're doing is we're simply finding the difference between my delta H of my products. So in other words, this would be the enthalpy of formation of my products. All right? And I'm going to be adding the enthalpy of formation, which remember is going to be opposite because it's not really forming, it's breaking. All right? And so what we end up with is a total delta H of this reaction of negative 3,121.2 kilojoules per mole. Again, we put in 167.6 kilojoules per mole to break apart my reactants. We got out 3,288.8 kilojoules per mole to form my products, which means in sum, again, it's like money. If I give you $1 and then you give me 10, I only got $9, right? So in other words, my net change, my delta change of money would have been $9. In this case, we put in 167.6, we get out 3,288.8. So the return on this entire reaction, so the delta H of this entire reaction in this case is going to be negative 3,121.2 kilojoules per mole. So that wraps up today's video. Let's do a quick recap. Today, we first learned about what is the heat of formation of any one compound and how it's associated with the Hess's law that we talked about in the last video. We also then used the enthalpies of formation from varying compounds to be able to then predict the delta H of a reaction that incorporated those as reactants and products. I'd like to thank Sam Dyer and Jack Rufo for writing, filming, and editing this video. I'd like to thank you guys for watching it, and I'll see you in the next one.